This question is taken from the ENGAA 2020 Section 1 paper. It is question 33. So we read, a tennis ball has speed 24 meters per second and is then hit by a racket. The ball goes back along its original path and the change in velocity is 48 meters per second. So it should go back the other way with the reverse speed, so minus 24, for example. The acceleration of the ball whilst in contact with the racket is constant and has magnitude 6,000 meters per second squared. What is the total distance travelled by the ball whilst in contact with the racket? So immediately we think we're trying to calculate a distance, so distance that the ball travels. And so it will be going into the tennis racket and getting slowed down, and then as it's slowed down to 0, then it's getting pushed back out, and then so we can split the distance into two parts with suvat. This is how we should do it, because we're given this acceleration and velocities. So if we draw the setup, then we know that we have u equals 24 originally, and then the acceleration is minus 6,000, let's say, going the other way. So it's slowing it down initially and then accelerating it backwards when it's pushing back out. So we have u and we have a, and we're trying to calculate displacement. So there's no obvious choice for time, but we do know, as we're splitting it into two parts, that we're slowing it down to 0 first. So we have v squared equals u squared plus 2as, and then we can use v equals 0 in this equation. So 0 equals 24 squared minus 2 times 6,000 for the acceleration times s, and then rearranging this, we get s equals 24 times 24 over 2 times 6,000. So breaking it down into this is really useful for cancellations and simplifying, because we don't want to work out 24 squared exactly, because that, even if you can do it, it's quite long. And then now we can cancel out some terms, so 12 and 4 here, and then we get 1,000 left on the bottom, so with these cancellations. So this is 48 times 10 to the minus 3, which is 4.8 centimeters in this process. So this is from the ball traveling initially at speed u equals 24 and then getting slowed down to 0. So that's the first part, but how would we calculate the second part when it's getting pushed back out, that distance? Well, there's two ways to think about this that give you the same answer. From symmetry, we've gone from u equals 24 to 0, and then the next part will be u equals 0 to v equals minus 24, for example. And this distance should be the same as the initial one. And you can see this from the equation v squared equals u squared plus 2as. So whenever we interchange these, we will just get a negative displacement, because in one case we're going one way and then the other is just starting from 0 going out the other way, ending at speed of v equals minus 24. So from symmetry grounds, or just through thinking about this, we can see that the displacement going back the other way should be the same. So 4.8 centimeters times 2 gives us 9.6 centimeters. This is a really useful property, and I cannot emphasize it enough, that in SUVAT a lot of the symmetry you can use, especially in projectile motion as well, in some other questions, you can make huge simplifications using this, rather than having to work everything out all over again.